students, I am Mrs. Paul NR from SGM College, Karad. Today we are going to see the physical properties of transition elements. Physical properties of transition elements. As all transition elements are metals, physical properties of transition elements are the properties of metals. Then what are the properties of metals? Metals are malleable, flattened to thin sheet. ज्याचा पत्रा तयार करतात, ductile, which have ductility, तन्यता, तार तयार करता येते. Metals are malleable, ductile, good conductors of heat and electricity. They can form the alloys with other metals. These are the properties of the metals, and that are the properties of transition elements also, because they are metals and these are hard also. Thus all the transition elements or other transition metals have physical property, that is the malleability, ductility. They are good conductors of heat and electricity. They can form alloys with another metals. These metals are the hard metals. Then some other properties. In 3D series, the last elements are zinc, mercury, cadmium. Zinc is the last element in 3D series. Mercury is the last element in 4D series. Cadmium is the last element in the 5D series. Except these three elements, all transition metals are very hard and have low volatility. Why all transition metals are hard and these are some soft as compared to others? Because in remaining elements there are half-filled d orbitals, and due to these half-filled d orbitals, they can form the strong covalent bonding as well as the metallic bonding. Hence, which are remaining ones are the hard metals. And in case of zinc, mercury, cadmium, helium, the 3D orbitals is completely filled. That is 3D 10, 4D 10, 5D 10, etc. And due to this, the possibility of covalent bond formation is very less in these elements, and which are at the last of the series, and hence they are not so hard as these metals. Similarly, all the transition metals have a particular metallic structure like a HCP, hexagonal closed pack, or CCP, cubic closed pack, or body centered cubic structures, except zinc, mercury, cadmium, and manganese. Except these four elements, all other elements or all other transition metals have a characteristic metallic structures. As these metals are hard, heavy, these metals have high melting point. These are the physical properties of the transition metals. Melting point we will discuss again later. Then trends in atomic properties. Trends in atomic properties of transition elements. First trend is atomic and ionic radii. We have seen these trends in periodic table in 11th standard. आपण 11वी ते ट्रेंड्स बघितलेले आहेत. Atomic and ionic radii. In all all transition elements from when we go left to right. Atomic number increases. As atomic number increases, means nuclear charge increases and outer electrons also increases. Effective nuclear charge also increases and attraction between nucleus and electron increases, and hence from left to right the atomic radius decreases in general. In d block elements or in transition series also, atomic radius decreases from left to right. There is a decrease in atomic radius, but there is a gradual decrease or slow decrease in atomic radius. Why there is a slow decrease? Because as atomic number increases, nuclear charge also increases, but last electron enters not in outermost shell, but it enters in n-1 shell or n-1 d orbital, and which has smaller screening effect. And due to this smaller screening effect, the atomic radius decreases, but this decrease is slow decrease or gradual decrease from left to right. Similar trend for the ionic radii also. Ionic radii is also decreases from left to right, but with some irregularities. If there is elements with the same oxidation state, consider the element M, same element with different oxidation state, that is M plus 2, M plus 3. These are the cations of the same element, but they have different oxidation state. Then the cation which have higher size have the smaller atomic radius than the cation which have the smaller charge. M plus 3 has smaller atomic radius than the M plus 2. This is the ionic radii of transition elements are smaller than the ionic radii of representative elements in respective period or in same period. Means if we consider the ionic radii of transition elements in the fourth period, then ionic radii of the transition elements of fourth period are less than the ionic radii of the S block elements or the P block elements in the same period. That S and P block elements are called as the normal elements or the representative elements. This is the trend in the atomic or ionic radii, that is, in short, atomic or ionic radii slowly decreases from left to right with some irregularities. Then next one is the ionization enthalpies. What is ionization enthalpy? Ionization enthalpy means amount of energy required to lose the most loosely bound electron in the outermost shell. outermost शेल मधला इलेक्ट्रॉन काढून टाकण्यासाठी लागणारी एनर्जी म्हणजे आयोनायझेशन एन्थॅल्पी. Amount of energy required to lose the electron from outermost shell to form the cations is the ionization enthalpy. What is the IE1, which is called as the first ionization enthalpy? IE2 is the second ionization enthalpy. IE3 is the third ionization enthalpy, and so on. What is IE1? Means amount of energy required to remove the most loosely bound electron from outermost shell to form the monopositive cation is the IE1. Means if one electron loses, it got the +1 charge, and energy required to lose that one electron is the IU1. If there is a formation of the M plus ion, cation is called as the ionization enthalpy 2 or IE2. That means if energy required to remove the electron from M plus ion, there is a formation of cation फॉर्म झालेला आहे. कॅटायन पासून एक इलेक्ट्रॉन आणखी रिमूव्ह करायचा असेल तर तो रिमूव्ह करण्यासाठी लागणारी एनर्जी म्हणजे सेकंड आयोनायझेशन एंथॅल्पी. and it is difficult to remove the electron from the cations, hence IE2 is always greater than the IE1. when second electron is removed, then there is a formation of the M plus 2 ions because there are the 2 electrons are removed from this neutral atom. As 2 electrons are removed, there is a formation of the 2 positive charges. What is third ionization enthalpy? Third ionization enthalpy means amount of energy required to lose the electron from the dipositive cation, and this is called as the third ionization enthalpy. The energy required to remove the electron from dipositive cation is always higher because it is difficult to remove the electron from the positive ions than from the neutral atom. Hence, always IE2 is greater than IE3 is greater than IE2. Thus, IE3 is greater than IE2, which is greater than IE1. This is the first ionization enthalpy, second ionization enthalpy, and the third ionization enthalpy. In case of transition elements, as atomic radius decreases slowly from left to right, ionization enthalpy increases slowly from left to right. It is opposite to the atomic radius. But in case of ionization enthalpy, there is increase in ionization enthalpy, but this increase is slow or there are some irregularities when increase in ionization enthalpy of 3D transition series. That first increase slowly, then increase, then decreases. That is, there are some irregularities in increase. In case of ionization enthalpy of 3D, 4D, 5D, 6D series, means these are the elements from top to bottom. 3D series first, then 4D, and according to periodic table, we know as it is expected that as we go from top to bottom, atomic radius increases, and as atomic radius increases, ionization enthalpy should be decreased. It is the expected, not observed. Ionization enthalpy should be decreased because ionization enthalpy is inverse to the atomic radius. But actual case, in case of transition elements, the 5D series, that the third series have the higher ionization enthalpy than the 3D and 4D series, that is the first and second series. What? Again, I am repeating, that is, it is expected that from top to bottom ionization enthalpy should decrease, but actually ionization enthalpy of 5D series is higher than the ionization enthalpy of 4D or 3D series. Why this 5D series has higher ionization enthalpy? Because in case of 5D series, if we see the electronic configuration of any 5D element, in that 4f orbitals are completely filled, that is the 4f14. And as 4f orbitals are completely filled, due to this filled 4f orbital which have the poor shielding effect or poor screening effect, due to poor shielding of this 4f orbital, attraction between the nucleus and nucleus and outer electrons increases due to this completely filled 4f orbital. As attraction increases, the outer electrons somewhat tightly held, and hence more energy is required to remove the electron from such an outermost shell for the 5D series, and hence the 5D series or 3D series or 5D series or third series in transition elements have higher ionization enthalpy than 3D and 4D series. In short, 5D series have higher ionization enthalpy than 3D and 4D, because in case of 5D series, 4f orbitals, inner 4f orbitals are completely filled, and due to completely filled 4f orbitals which have poor shielding effect, attraction between nucleus and outer electrons increases, that outer electrons are somewhat tightly held, and hence more amount of energy is required to lose these electrons, and hence this 5D series or third series has higher ionization enthalpy than the first and second series. Then the next property is the metallic character. Metallic character of the transition elements or transition elements. Due to low ionization enthalpy and vacant d orbitals in outermost shell, the transition elements have metallic character, and these are responsible, transition elements are responsible for the metallic character. In case of transition elements, consider 3D series from scandium to manganese. Number of unpaired electron increases and then number of unpaired electron decreases. We are seen in the last lecture. As number of unpaired electron increases in 3D orbitals, the possibility of covalent bonding in atoms is also increases. More the number of unpaired electrons, more of the covalent bonds, and stronger is the metallic bond also. In case of transition elements, there is a covalent bonding as well as metallic bonding and perfect crystal structures or metallic structures for that elements. That elements have the particular metallic structure or the particular crystal structure, as well as they show the metallic bonding, as well as they show the covalent bonding. And as number of unpaired electron increases, number of covalent bonds increases, the stronger is the metallic bond also. Metallic bonding is due to the vacant d orbitals as well as the number of unpaired electrons, and due to they have the crystal structures. Thus, all the transition elements shows the metallic characters. Why these have metallic character? Due to three reasons. One is the due to number of unpaired electrons, which shows the covalent bonding. Then second is the which shows the metallic bonding also, and third is the which have the particular metallic structures or the crystal structure like the hexagonal close packed, cubic close packed, body centered cubic packed, etc. And as atomic number scandium, atomic number 21 configuration is 3D1 4s2, titanium 22 3D2 4s2, and so on. Means number of unpaired electron increases from scandium, titanium, vanadium, chromium, and manganese up to manganese. Here 3D 4s2, here 3D 5 exceptional 4 5 4s2. As number of unpaired electrons, we can write this 3D as 1 2 3 4 5. 3D1. It can form the one covalent bond with this 4s2. One covalent bond with the another atom. If there are two unpaired electrons, it can form the two covalent bonds with another atom. Thus, number of unpaired increases up to manganese, and means number of unpaired electron increases, number of covalent bonding increases, and its metallic bond also becomes stronger, which are more strength, and hence it becomes more harder, and melting point of such a transition elements are also increases as number of unpaired electron increases. Hence, in case of 3D elements, if you plot the melting point versus atomic number, then as number of unpaired electron increases, melting point increases. Means melting point increases like this, and then melting point decreases. This is the chromium with number of unpaired electron 5 in 3D series. Chromium has the atomic number 24, but number of unpaired electron 5, and which has highest MP. Exceptionally, manganese has low MP, which has also 5 unpaired electron, but manganese has not a perfect crystal structure or metallic structure, and which has the low MP, but chromium has the highest MP in 3D series. In 4D series, have higher MP than 3D series. Molybdenum has higher MP in 4D series, and in 5D series, tungsten has higher MP. Thus, in 3D series, chromium has highest MP because of higher unpaired electrons. In 4D series, molybdenum has highest MP, and in 5D series, tungsten W has the highest MP. This question may be asked to CET or the Maharashtra State Board, that is which element in 3D series have highest MP. Then chromium has the highest MP. In 4D series, molybdenum has highest MP. In 5D series, tungsten has highest MP. And in all these, the tungsten has highest MP in 3D, 4D or 5D series. This is the metallic character of the transition element, that is metal. In short, metallic characters are due to number of unpaired electrons, that is due to covalent bonding as well as due to metallic bonding, and due to the metallic structure or crystal structures of the metals, crystal structures of the 3D elements. Then next property is the magnetic property. Very simple to remember, but very IMP. Mostly questions are asked on the magnetic properties, to calculate the magnetic properties of these. Then how to calculate the magnetic properties? The spin only formula for calculation of the magnetic properties is mu, that is the magnetic moment. Mu is magnetic moment equal to n into n plus 2. Mu equal to under root of n into n plus 2 Bohr magneton. See again, this mu is the magnetic moment, where n is the number of unpaired electrons in that particular cation or in that particular atom, and Bm is the unit for that, the Bohr magneton. Magnetic moment can be calculated by using this formula, mu equal to n into under root of n into n plus 2 Bohr magneton. Now, I will take one example. Calculate the spin-only magnetic moment of divalent cation. Calculate spin-only magnetic moment of divalent cation of transition element of divalent cation of transition element with atomic number 26. We have to see the example again. Calculate spin-only magnetic moment. This formula is mu equal to under root of n into n plus 2 of divalent cation of transition element with atomic number 26. Divalent means which has two valency or which has plus 2 oxidation state. Atomic number 26. The element with atomic number is iron, Fe. Or if we don't know the element, we can understand the electronic configuration of the 26. As atomic number 26, its outer electronic configuration is 3d6 4s2. Atomic number is 26. Or iron with atomic number 26, outer electronic configuration is 3d6 4s2. It is a divalent cation. Means two electrons are lost from the outermost shape, that is Fe becomes the Fe plus 2. Or say only divalent cation. Electronic configuration of divalent cation becomes by losing 2 electrons. Electronic configuration becomes 3d6. As Fe plus 2, electronic configuration becomes only 3d6. Calculate the number of unpaired electrons in this 3d6. 3d6 means you can write this 1, 2, 3, 4, 5. 3d6, 1, 2, 3, 4, 5 and 1 electron get paired. How many unpaired electrons in 3d6? 1, 2, 3, 4. There are the 4 unpaired electrons. Thus we can calculate the magnetic moment by using the formula mu equal to under root of 4 into 4 plus 2 Bohr magneton Bm. Under root of 4 plus 2, that is 6. 6 into 4, that is 24. Then by calculating this under root of 24, it is the 4.9 Bohr magneton. Remember, this is 24, means near about the 25. Square root of 25 is 5, means answer should be near about 5. हे 24 चं वर्गमूळ आहे. आपल्याला 25 चं वर्गमूळ 5 असतं. 25 चं वर्गमूळ किती आहे? 5. म्हणजे 5 च्या आसपास याचं उत्तर आलं पाहिजे, आन्सर आलं पाहिजे. Which should be near about 5. This is the trick for the remainder. If we take another example for that, consider any, that is the Mn2 plus. Calculate the magnetic moment of dipositive cation, dipositive ion of the manganese or atomic number 25. As manganese has atomic number 25. Its electronic configuration is 3d5 4s2. Atomic number 25. Electronic configuration 3d5 4s2. For Mn plus 2, these 2 electrons are lost. Therefore, configuration becomes 3d5. That means 1, 2, 3, 4, 5. One electron in each orbital, that means all the 5 electrons are unpaired. Hence, for calculation of magnetic moment of Mn plus 2, mu equal to under root of 5 into 5 plus 2. 5 plus 2, 7. 7 into 5, 35. Bohr magneton. It should be, as it is 35, it is near to the 36. This answer should be near about 6. This is the trick. And its answer is the 5.9 Bohr magneton. This is the magnetic moment, characteristic of the transition element, that is the magnetic moment. Thus we see the different characters, atomic and ionic radius. In short, atomic radius decreases left to right, ionic radius also decreases, ionization enthalpy increases slowly with some irregularities. Ionization enthalpy of the third series is higher than the first and second due to poor shielding effect of the 4f orbitals. Then metallic characters are due to unpaired electrons, that is due to the covalent bonding, metallic bonding and perfect metallic structures. Magnetic moment can be calculated by using the formula under root of n into n plus 2. In next lecture, we are going to see the color of the transition elements as well as the interstitial compound and catalytic properties. Thank you.